All right, I'm going to turn it over and let you guys get running with it.
Okay, I'm going to go ahead and share screen. And hopefully everyone is seeing just the one slide. Can someone confirm that?
Yep, looks good.
Wait a minute, I just realized I didn't do something right here. Hang on, let me do that again. There we go. Hopefully still have it.
Looks
Yeah,
good.
you do.
All righty, very good. Okay, so today's topic is safety. It's going to be 3 different safety topics: power circuits and hazards, antenna safety, and RF hazards. There's 36 of the 412 questions in the pool relate to safety, and the exam will have 3 questions from these topics. And as with all of the topics and classes, just attending the class is probably not going to be enough to ensure passing the exam. Should be spending a number of hours outside of this one study, and we strongly recommend using hamstudy.org in the practice mode. I know you've heard that a number of times, but can't emphasize it enough. So the first section on power circuits and hazards, there's a number of subtopics listed here: hazardous voltage, fuses and circuit breakers, grounding, electrical code compliance, lightning protection, and battery safety. And then the second section covers antenna safety, both including tower safety and grounding, and installing of antennas and antenna supports. And then the last topic is RF hazards, radio frequency hazards, radiation types, radiation exposure, proximity to antennas, recognized safe power levels, and the concept of duty cycle we will be talking about. So let's delve into the first subtopic of power circuits and hazards, and a little example of that coming up.
And I can't even feel it because the voltage is not high enough. Wow, this is wild. You can see how far this gap is quite wide. Let me measure it for you. Some toothpaste and you're ready to go. It's a very simple and yet effective circuit. Let's turn it on. The skin here is quite sensitive to temperature and you can tell the temperature quite accurately. This is not the best way and you might like to try a safer way. Oh, and don't drop the iron on your pants. It's almost finished now. Just need another piece of wire. What did I do?
What the f*** did you do?
I'm fine, thanks.
Idiot.
What? The tip of the gun here simulates a human finger. Always be careful with your tools. That side needs to be connected to ground or negative. It doesn't give me an electrical shock when I do it with my finger. Ow! Ow! But it burns my skin into a charcoal. I made this simple circuit and I'll plug it in. Now the circuit is hot and the voltage is on this. To measure the 120 volt AC, I put the meter on AC and I measure the voltage. Oh my God! I thought I could share my artistic side with you.
Anyway, that's some examples of what we don't want to be doing, obviously. Let's talk a little bit about hydrogen. This is an example of this facility here in the picture was used to be a large computer data center with a battery room and emergency generators in Sacramento, California. The company had vacated the building and moved out the computer equipment and everything, but they left the battery backup system behind. The ventilation for the battery room appeared to have been tied to a hydrogen monitoring system, which is a common practice. And the hydrogen sensor was in an alarm, was alarming at the time the emergency responders arrived. 911 callers reporting the explosion also reported hearing an alarm for 3 days prior to the explosion. But apparently the alarm was just a local alarm and didn't go to the fire department. Given how slow batteries generate hydrogen gas, it must have been charging for a long period of time with no ventilation. So they think the ignition was caused by where a grounding strap was connected, got a spark somehow. But the lesson is that ventilation is critical when you're dealing with lead acid batteries because they do generate hydrogen. Let's take a look at station grounding. You can see in this illustration here, we've got your grounded electrical outlets. That's one thing, but you want to have a common RF ground to reduce the hazards with all your equipment. You can see they've got the transceiver and some various other things connected to a ground bus, in this case, a copper pipe, which then is connected to a ground rod that's in the earth. So you want to keep these runs to a minimum. They should be short and straight and direct to ground, which reduces possibility of RFI as well. So lightning arresters, we don't, here where I am in Western Washington, lightning is not a big concern like it is in a lot of parts of the country, but it is a concern. And basically a lightning arrestor protects the equipment from the power surge that you would get with the lightning traveling down the through the antenna down the coax feed line, and eventually, if you don't have lightning arresters, into your shack and into your equipment. And since you don't want this getting into your home or your building, lightning arresters should be installed with a grounded panel where it enters the building, not inside. So that's where you would want to have your grounding or your lightning arresters. All right, so let's take a look at some quickly definitions here that will come up during these topics. They're pretty straightforward. Alternating current, FAA, Federal Aviation Administration, FCC, Federal Communications Commission. HZ is hertz, seen that before. RF, radio frequency. SWR, standing wave ratio. UL is the underwriter's laboratory, and of course, V for volts. So I'm going to go through the questions in a different order than they are listed in the question pool. I've grouped them generally by the subtopic so that we've got related questions together. It's a little more logical way of approaching it, in my opinion. So here's the first general question we've got about electricity. What health hazard is presented by electrical current flowing through the body? Does it cause injury by heating tissue? Does it disrupt the electrical functions of the cells? And might it cause involuntary muscle contractions? Well, as a matter of fact, it does all of those things. Not good. Next question. Which of the following is a safety hazard of a 12-volt storage battery? Okay, this one you might think A is the best answer, but it's a good answer, but touching both terminals can cause electric shock. That's possible. But shorting the terminals can definitely cause burns, fire, or explosion. And RF emissions from a nearby transmitter can cause the electrolyte to emit a poisonous gas. That is not correct. So it can't be all of the above. So the best choice among A and B would be B. Shorting the terminals can cause burns, fire, or an explosion, as illustrated. All right. What hazard is caused by charging or discharging a battery too quickly? All right. Remember the first picture we saw there of that facility in California. What happened? Hydrogen gas emission. So discharging a battery too quickly, we're worried about overheating or outgassing, emitting hydrogen gas. The other answers really don't relate to charging the battery. What is the purpose of a fuse in an electrical circuit? Okay. To prevent the power supply ripple from damaging a component, remove power in case of an overload, limit current to prevent shocks. Well, it's this the ripple question is a red herring. Removing power, that's what a fuse does. Fuse blows, it breaks the circuit and it removes the power from the circuit. Power doesn't flow anymore. So the correct answer is B. Remove power in case of an overload. With that in mind, the next question, why should a 5 ampere fuse never be replaced with a 20 ampere fuse? So remember that a 5 amp fuse will blow when it exceeds 5 amps current, or it's a 20 amp one will not blow until the current exceeds the 20 amp, the rating of the fuse. So A, the larger fuse would be likely to blow because it is rated for a higher current. No, that's the exact opposite. The power supply ripple would greatly increase. Now, that's the red herring. And we already know that A is not true, so D cannot be true. The answer is excessive current could cause a fire. Okay. Where should a fuse or circuit breaker be installed in a 120 volt AC power line? Okay. Fuses are always going to be in series, not in parallel, so you can eliminate C and D because you want it in the circuit so that when it blows, the circuit is disrupted. If it was in parallel, the current could flow around it. So it's got to be either A or B, and it's going to be in series with the hot conductor for an AC power circuit. Next question, what is a good way to guard against electrical shock at your station? Use 3-wire cords and plugs for all your AC powered equipment. Well, we always want to do that. You saw that illustration of the grounding. We had the 3-prong outlets as part of the, system. B, connect all AC powered station equipment to a common safety ground. And that's what that pipe was our common ground. Or C, install mechanical interlocks in high voltage circuits. Well, we've just said looks like A and B are correct. So is C correct, which would mean all of the above are? Well, yes, if you have a mechanical interlock in a high voltage circuit. So if you open up, for instance, a cabinet containing a high voltage circuit, if you have an interlock, when you open the door, it'll shut off the circuit so you can't be exposed to the high voltage. So yes, that would be a good way to guard against electric shock in your station. All of the above. In the United States, what circuit does the black wire installation indicate on a 3-wire 120 volt cable? All right, so it's either going to be neutral, hot, equipment ground, or black is never used. Well, the answer is hot. DC circuits, and we're talking about an AC circuit here. DC circuits, black is usually going to be minus or ground, and red is going to be positive. But in AC wiring, black is the hot line, white is neutral, and green is ground. Okay. What hazard exists in a power supply immediately after turning it off? Circulating currents in the DC filter, leakage flux of the power transformer, voltage transients from kickback diodes, or charge stored in filter capacitors. Remember what a capacitor does. It holds an electrical charge. That is your answer. After you turn off the power supply, there will still be a charge in the capacitors, and you don't want it to discharge through you. Okay. Which of the following precautions should be taken when measuring high voltages with a voltmeter? Ensure that the voltmeter has a very low impedance. Ensure that the voltmeter and leads are rated for the use at the voltages to be measured. If you're going to use a voltmeter that's only rated for a 10 volts and you're going to put it on a 1,000-volt circuit, that's obviously going to burn up your meter. Ensure that the circuit is grounded through the voltmeter. You don't want to ground it through the voltmeter. And ensure that the voltmeter is set to the correct frequency where there are no frequency settings on a voltmeter. So the answer is going to be B, ensure that the voltmeter and leads are rated for use at the voltages to be measured. It's kind of a common sense answer. Use equipment that's rated for what you're going to use it for. Where should a lightning arrestor be installed in a coaxial feed line? Well, we talked about that at the very beginning of this section. It's going to be on a grounded panel near where the feed lines enter the building. You want to keep the lightning out of the building. So if we're at the output of the output connector of the transceiver, it's already too late. You've already got it flowing into your shack. At the antenna feed point, you think, oh, well, that's outside. That would be okay. But then you have the entire feed line that would not be protected. And at the AC service panel, well, that's not going to help you any with the coax coming in. It's not going through the service panel. So grounded panel near where the feed lines enter the building. All right. One more question in this section. What should be done to all external ground rods or earth connections? And we haven't really talked about that. We're going to talk about this more on towers, and maybe I should have moved this question to the tower section, but what do we want to do with external ground rods? Well, we saw that ground rod was connected to the grounding strap that went into the grounding bus on the station, and that illustration at the very beginning. Well, waterproofing them with silicone or caulk, I don't know what that has to do with anything. Keeping them the rods as far apart as possible, there's not necessarily a reason to have them. It depends on what your installation is. You want to bond them together with heavy wire or conductive straps. This is the key. With grounding, you want everything to be at the same potential. So anything that's part of your grounding system, you want connected together so that they have a common potential. So the answer is bond them together with a heavy wire or conductive strap. Okay. Any questions on this first section so far? All right, well, then we'll move on to antenna safety. Doesn't look like that antenna fared too well. So we're going to talk a little bit about crank-up towers. This is what we're talking about with a crank-up tower. It's got different sections, usually a cable running up in the inside that either manually crank or it's motorized crank of some kind that pulls up each section until it extends to the full height, and then can be lowered back down. You can see it's in the lowered position on the right, extended position on the left. So things to remember about tower work is the illustration in the upper left there is you see a power line. You don't want to be near power lines. Obviously, anything at height, you're going to want to have a harness, an appropriate safety harness. And you can see doesn't look like he's exactly wearing a safety harness on the right. So tower base and grounding, we just talked about how we wanted to bond components of a grounding system together. Here's an example of a tower base and the grounding for it. You can see probably better in the lower right where the drawing is, where you've got ground rods in the ground, and then you can see that grounding ring. That is the straps or wire, whatever you're using to connect to bond each of the rods together, and then each of the rods is connected to the leg of the tower. So you want to have you want to have 3 ground rods. The ground rods need to be 8 feet long, which is really long. You think about it, and some of our soil, or at least here in Western Washington, trying to drive down 8 feet can be a bit of a problem. But again, you want everything the same potential, grounding, straps, rods, everything bonded together. Okay, so the first question, which of the following is a good practice when installing ground wires on a tower for lightning protection? Well, you can look at B and C here. Make sure all ground wire bends are right angles. And the second one, and C says make sure they're short and direct. Well, those are kind of contradictory. And as remember, we mentioned at the very beginning there, you always want to keep ground connections short and direct as much as possible. That's the answer. The drip loop has got nothing to do with the lightning protection. All right. Which is a proper grounding method for a tower? Okay, we just saw that in the illustration. The base, it's going to be 8-foot ground rods. Remember, 8-foot ground rods, one for each. You need them for each leg, and you need them bonded to the tower and to each other. All right. Which of the following is true when installing grounding conductors used for lightning protection? Okay. Remember what we said about all these grounding? We want them straight and direct, right? So that would mean that we would not be routed at right angle bends. We would want sharp bends to be avoided. And we do want common grounds. We don't want them to be avoided. We want everything to be at the same potential. So the answer is sharp bends. It doesn't matter whether the wire is insulated or not. All right. Which of the following establishes grounding requirements for an amateur radio tower antenna? This one is a little tricky because a lot of these answers would seem like they might be right. You would think, since it has to do with ham radio, FCC Part 97 rules would apply, but they don't address it. FAA tower lighting regulations. That's just aircraft safety so they can see it. That doesn't have anything to do with grounding requirements. UL, we see a lot of UL Underwriters Laboratory certifications on things electrical, and they may have practices, but that's not what controls what you're required to do. What you're required to do is determined by your local electrical codes. And most places usually have adopted the Uniform Electrical Code. That's their National Electrical Code. That's maybe with some local adaptations, but that's what governs. It's the local electrical code. What is required when climbing an antenna tower? Okay. Have sufficient training on safe tower climbing techniques. That sounds like a good idea. Use appropriate tie-off to the tower at all times. Well, you do want to be connected to the tower so you're not going to fall off. Always wear an approved climbing harness. Well, we talked about that. So I guess all of these are good choices, aren't they? So all of the above in this case. Under what circumstances is it safe to climb a tower without a helper or an observer? Well, is it safe if there's no electrical work? If it's safe if there's no mechanical work? If it's safe, it's not more than 20 feet above ground? Well, the answer is no. It's never safe to climb a tower without a helper or an observer. This is a two-person operation. Something happens, you need somebody there to assist. Which of the following is an important safety rule to remember when using a crank-up tower? Remember we talked about how you crank a cable and it pulls up each section? It says this type of tower must never be painted. I have no idea what painting would have to do with it. This type of tower must never be grounded. Well, we always want towers to be grounded, right? So we've now eliminated the first two, which eliminates D, and the answer is C. This type of tower must not be climbed unless it is retracted. So if it's all the way down so that it can't fall, it can't move down, or a mechanical safety locking device has been installed, so something that will physically prevent it from retracting while you're on it. So that's your answer. All right. Which of the following is an important safety precaution to observe when putting up an antenna tower? Okay, so we're going to put up a tower. Wear a ground strap connected to your wrist at all times. You might want to do that if you're working in an electronic circuit, but not putting up a tower. Insulate the base of the tower to avoid lightning strikes. Well, insulating the base isn't going to do anything. It has nothing to do with putting up the tower safely. Look for and stay clear of any overhead electrical wires. Clearly the answer. If you're raising up a tower, you want to make sure you don't touch overhead electrical wires. That will ruin your whole day. All righty. What is the purpose of a safety wire through a turnbuckle used to tension guy lines? This is a tough question. I think a lot of people won't even understand what they're talking about here without an illustration. So let's take a look at an illustration. Here's an example of it. And the answer is to prevent loosening of the turnbuckle from vibration. You can see here that you've got, let me get my cursor up here. So here's your turnbuckle. Here's where the safety wire is going through. And you see there's a little hole here. And it prevents this from rotating and loosening. Because once you've tightened it up to, this is how you tighten up the turnbuckle. And once you've got it to where you want it to be, you need to put that safety wire in so it doesn't loosen up from vibrations or whatever might loosen it. All right, let's see if I can get my next slide up here. There we go. What is the minimum safe distance from a power line to allow when installing an antenna? So you got an overhead power line, you're going to put an antenna up. How far away do you really need to have that antenna? So there's a lot of answers here that look like, gee, that might make some sense. Just take them in a different order. C, half wavelength at the operating frequency. Well, falling into your concern is, are you going to hit a power line? So what frequency you're operating on isn't going to affect how far away you need to be to prevent it from physically hitting the power line. So C is out. The safe distance would be the height of the power line. Well, what if you have your power line is up 50 feet in the air and you have a 5-foot antenna? Why would you need it to be 50 feet away? It's not going to hit that wire, right? The height of the antenna, the height of the antenna to the height of the power line, and multiply a factor by 1.5. Well, that sounds like an interesting formula, but it's simpler than that. The answer is going to be D. You want it to be far enough away so that the antenna falls. No part of it can come closer than 10 feet to the power line. So depends on how tall your antenna is going to be, but you want to figure out how tall is your antenna. You don't want it, if it falls, to come any closer than 10 feet to where the power lines are. And that's how far you would want to move it away. Okay. It's actually a fairly logical answer. Why should you avoid attaching an antenna to a utility pole? Okay. It won't work properly because of induced voltages. Remember, this is a safety question. The 60 hertz radiations from the feed line may increase the SWR. The antenna could contact high voltage power lines. What's on a utility pole? High voltage power lines. So the answer is the antenna could contact the high voltage power line. Another good reason not to do it is it's usually against the law to do that, to attach things to the power company's power poles, and they will not be happy, and if they have to remove it, they're going to send you a bill for it. So another good reason not to do that. All right. Any questions on that section of the question pool before we move on to RF hazards? some of these things are a bit common sense. Now let's talk a little bit about RF hazards, radio frequency hazards. Now remember, there's different types of radiation. You can see on this kind of busy slide here, we're looking at the wavelength towards the top there, the longer wavelengths, the lower frequencies to the left, higher frequencies, shorter wavelengths to the right. And you can see where the radio frequency spectrum is in here, microwave up here, VLF, ELF, really low frequencies. You get up higher frequencies, you're into the visible light range, ultraviolet and on up to X-rays and gamma rays. Now, the RF has frequencies above visible light range, above ultraviolet. So this is your X-rays and gamma ray area. This is called ionizing radiation. Everything lower in frequency than that is non-ionizing. And by ionizing, we mean that it can damage the DNA of your cells. And therefore, it's extremely hazardous. So just think about X-rays or, radiation from nuclear weapons, things like that definitely cause cellular damage. Okay. So looking here at the power thresholds for that the FCC requires a study for and requires that you take note of. You can see that these power levels, the transmitted power that's permitted before you need to do a detailed study, varies with the wavelength or the frequency of the RF energy. And you can see here that the lowest allowed power levels are in the 10 meter to 1.25 meter range. VHF range primarily is where you're allowed the least amount of power exposure, because that is the frequency at which the human body is affected more, absorbs more, is more sensitive to the radiation in those frequency ranges. So these different power levels are what trigger a need for a station evaluation. So let's talk a little bit about duty cycle. Duty cycle is basically the ratio of the time that you're transmitting versus the time that you're receiving. Or first, it's actually the transmit over the total time. So if you talk about 40%, like the first one here, CW Morse lasers, it's 40% duty cycle. So out of a 1 minute period, a normal operation, 40% of that time would be transmission, and the rest would be receive only. Okay, so it refers to the transmit and receive time and the average power level during transmission. So CW has gaps, so it's a continuous wave, but it's not on continuously when you're doing Morse code. So it's going to be less than 100%. But you'll see that things like FM are 100%. So whether you're talking or not, if you have the mic keyed, you are at 100% transmission. Okay. So what we're interested in for exposure is what is the average amount of exposure you're getting over time, not the peak, but the average. So the average RF exposure times over 10 and 30-minute periods, you can see how these graphs illustrate that you're looking at the areas, shaded areas, as for what the average exposure amount is. So it could be continuous at a low level, or it could be not continuous, but at higher levels and end up with the same amount of exposure, which is what those are illustrating. So the vertical axis is the power level, time along the horizontal. As I said, the shaded areas represent the average exposure. And remember that the body is most sensitive to the VHF frequencies. So that's important to note. You'll see that in the questions. So let's look at some of these questions. What type of radiation are radio signals? Are they gamma, ionizing, alpha, or non-ionizing? Remember, everything below the visible light range is non-ionizing. That above is ionizing. Gamma rays are ionizing, they're above that. We haven't even talked about alpha, but it is non-ionizing radiation. Okay. How does RF radiation differ from ionizing? So the difference between ionizing and non-ionizing radiation. And as I mentioned, it's answer A here. RF radiation does not have sufficient energy to cause chemical changes in cells and damage the DNA. You don't get the cellular damage that you get with ionizing radiation. RF radiation is not perfectly safe. You can get a radiation burn. RF radiation is not just limited to a few feet, and I don't even know if there's such a thing as an RF dosimeter, but maybe there is. So the answer is A. It doesn't have the energy to cause the chemical changes to your cellular structure. What factors affect RF exposure of people near an amateur radio antenna? Frequency and power level of the RF field, distance from the antenna to the person, and radiation pattern in the antenna. Well, actually, all of these are correct. We already saw those charts that talk about the power levels versus frequency and how important that is. And logically, the farther away from the antenna you are, the less you're going to get exposed. But also the radiation pattern of an antenna is important. Remember, we took beam antennas and omnidirectional antennas. A beam antenna focuses energy in one direction. So if you're in the beam of that antenna, you're going to get more exposure than if you're in one of the null areas. So the radiation pattern also affects the exposure that one would have if they're near an antenna. Why do exposure limits vary with frequency? Lower frequency RF fields have more energy than higher frequency. Lower frequency fields do not penetrate the human body. Higher frequency fields are transient in nature. Or D, the correct answer, the human body absorbs more RF energy at some frequencies than at others. And that, remember that VHF is the one that's the body is most susceptible to. What hazard is created by touching an antenna during a transmission? One of the things that idiot in the video was doing when he touched, he said he didn't get electrocuted, but he got a bad RF burn. That's what you're concerned about, is RF burns. And it doesn't have to be really high power. You touch your mag mount antenna with a 50-watt mobile radio, when it's transmitting, you're going to get an RF burn. At which of the following frequencies does maximum permissible exposure have the lowest value? Another way of thinking about this is at what frequency are you most concerned about exposure, that you're most susceptible? So you got 3.5 megahertz, which would be your 80 meter band. You've got 50 megahertz is your 6 meter. You got 440 megahertz, your 70 centimeter, and 1296 megahertz up to your 23 centimeter. Well, remember we said VHF. That's where it is. VHF, 30 to 300 megahertz. So in the 50 megahertz is right in that range. So that would be where we would have the most concern. And so we would have the lowest maximum permissible exposure. Which of the following actions can reduce exposure to RF radiation? Okay, so if we don't want to get exposed, how can we? Well, we could move the antenna somewhere where it's away from people. Yeah, that would do it. Relocate the transmitter. Well, moving the transmitter doesn't have any effect because the radiation, the RF is radiating out of the antenna, not out of the transmitter. Could you increase the duty cycle? Would that help? Well, remember, an increase in duty cycle means more transmission time. So 100% duty cycle is transmitting all the time. 50% duty cycle is half the time. So increasing the duty cycle would only increase the radiation. So that can't be right. So the only right answer is A, relocate the antennas. All right. How does the allowable power density for RF safety change if duty cycle changes from 100% to 50%? I just kind of gave that answer away, right? So if your duty cycle is cut in half, it means you're transmitting half as much, okay? So it's not going to increase the is it going to increase or allow? Stop for a second. Is it going to increase the allowable density or reduce it? So if it's transmitting less, can you have a greater power density or a lesser power? You can have more because it's only transmitting half as much. So the answer is it increases the allowable power density by a factor of 2 because the amount of transmission has been reduced in half. Hopefully that makes sense. Why is duty cycle one of the factors used to determine safe RF radiation exposure? Does it affect the average exposure? Well, duty cycle does affect the average exposure. If you're only transmitting half as much, you're not going to get exposed on average as much. It affects the peak exposure. A duty cycle has nothing to do with peak. It's how long you're on and off. Takes into account the antenna feed line loss. No, it doesn't. It just takes into account how much you're transmitting. It takes into account the thermal effects of the final amplifier. No, it doesn't do any of that. It affects the average exposure to radiation because of the amount of time it is in the transmit mode. What is the definition of duty cycle during the averaging time for RF exposure? Well, the last several questions, we've said this over and over. It's the percentage of time that the transmitter is transmitting, right? That's the definition of duty cycle. So that's your correct answer. Which of the following is an acceptable method to determine whether your station complies with FCC exposure regulations? Well, we've already learned that the FCC has these permitted levels, but how do you ensure that you're meeting that? Well, there is a document, an FCC document called the FCC OET Bulletin 65, which basically explains how you determine whether or not you're meeting the requirements. You can actually do it with computer modeling based on your individual station. And you can also do measurement of field strength with equipment. You can measure the actual radiation at different distances from the antenna. So actually all of these are correct. And this is probably something you're just going to have to remember, I think. Not sure there's a good way of memorizing or remembering it other than memorizing it. How can you make sure your station stays in compliance with RF safety regulations? By informing the FCC of any changes made in your station. Well, telling them isn't going to ensure that you've complied, just telling them. By reevaluating the station whenever an item in the transmitter or antenna system is changed. Well, that seems to make sense, right? By making sure your antennas have low SWR. Well, SWR doesn't necessarily have anything to do with compliance with the RF safety regulations. So yes, you would want to reevaluate your station. If you change something, you got to look at it again and see if you're still in compliance. So answer B. There's actually a calculator that's on the ARL website and is on the Lake Washington Ham Club website. Actually, the ARL got it from the Lake Washington Ham Club. But you can go into the ARRL website and search for RF exposure, or you can go to the Lake Washington Ham Club website and look at the calculator that's on there. You plug in the frequency and the information about your station, and then it will tell you how far away from the antenna people need to be. It's a very handy tool. Think about this, who is responsible for ensuring that no person exposed to RF energy above the FCC exposure levels for your station? Who is responsible? Well, it sure isn't the FCC. They're going to come after you. You, the station licensee, are responsible. People who happen to walk by your antenna, they're not the ones responsible. You're the one operating it. And the local zoning board's got nothing to do with anything. So very simple. You are responsible as the station licensee for ensuring that no one is exposed to RF energy above those levels. Pretty straightforward. It's your station. It's your problem. All right. We're through those questions. Means we've gotten through all 3 sections of the question pool. Any questions on any of it? Is anyone still awake?
Well, I don't have any questions on it. Again, thank you for doing such a thorough overview of these questions. I really appreciate it.
I have a question. Is
Okay.
it better, is it, for transmitting purposes, is it better to have the larger density, like the 50% transmitting? Does that send a clear message?
This has to do with the mode of operation you're in.
Oh, okay.
So if you're in FM, frequency modulation, it's the frequency that's affected by your signal, by your voice, for example. The way your voice is transmitted is not by changing the amplitude or the intensity of the signal, but by changing the frequency of the signal. So if it's an FM signal, it's considered to have 100% duty cycle. As long as you're keying that microphone, it's transmitting 100% of the power. If you were on sideband, for example, that power level is going to vary with the amplitude of the signal, which is going to vary with your voice or whatever it is you're transmitting over. So that has to do with the mode. Obviously, if you're not turning on your radio as much, you're not going to get as much exposure, right? If you're not transmitting as much, you're not going to get as much exposure. This doesn't have anything to do with how well you're heard at the other end of a signal or anything like that. This is strictly talking about what the risk of exposure to the radiation is in proximity to the antenna. Does that help?
Yeah, that helps. How much radiation would you say an average person is exposed to just in their daily, everyday life? 24 hours a day?
I have no idea, but you get a lot from the sun. Well, I can tell you this, okay? A little story about my past life. I spent 20 years in the Navy, and my last ship was a nuclear-powered aircraft carrier, the Nimitz. And some of us were required to wear a dosimeter, which measures the amount of radiation you get. And the people that worked on the flight deck and were exposed to the sun got more radiation than the people that worked in the reactor compartment where the nuclear reactors were, because they were shielded. So you get a lot of radiation on a daily basis from the sun. And of course, it's spread out over time. I have no idea what the exposure rates would be for people, but we're more concerned here with a short period of time where you have a fairly intense amount of radiation. I'm sure it's, we're talking very much lower levels with the sunlight, but
is it unlikely that an amateur radio operator could reach radiation levels that are harmful?
Sure can. You can touch an antenna and you can get a burn from it. Absolutely. Absolutely. And one of the reasons, if you have an HT, you hold it up by your head, right, when you're talking to it. One of the reasons why your HTs don't typically have more than about 5 watts output on it is because if you have too much power output that close to your head, it's not good for you. You know, the scare everybody has about cell phones causing brain damage and all of that. It's the same concept. They don't necessarily do that, but it's the same concept. You would not want to have a higher power you wouldn't want to have a 50-watt HT up against next to your head, because you would be too close to that antenna and you would get excessive RF exposure that would be harmful.
So John, we need to wrap this up because we've got to get Dave's segment in here.
Yep. Is that any other questions? All right. Well, let me unshare my screen here so Dave can do his thing. There we go. Should be back. There we are.
I'm going to go ahead and stop the recording too, and then restart it when we start the new segment.